Okay. First of all, I would like very much to thank the organizers for inviting me to come, and it's a great honor and a privilege to talk at the conference for Freeman-Dyson. I'm planning, I would like to go over some of the history, and I'll try to do that very quickly, but I think it's important to show some are equivalent formulations of strong subadditivity, and in particular the role of the Wigner-Yanase-Dyson entropy. And then I will slow down. I give you a very brief, simple proof, and then I want to talk about a remarkable new result. Basically, 40 years after the anniversary of the proof of strong subadditivity, there were a number of new results, of which the most notable was Kim, who is a graduate student at Caltech's operator version, and then I will make some remarks on other new developments. Okay, so in 1927, 20 years before Shannon, von Neumann defined the quantum entropy of a density matrix, positive density operator of trace 1, as S of rho equals minus trace rho log rho, and its basic properties are that it's positive, and it's concave, and it satisfies this inequality for composite systems known as strong subadditivity. And now if you can raise the board there, and there's, okay. So I'm not very good. Usually I have my junior co-authors make the graphs, and I thought I could do something this simple in Mathematica, but in fact I couldn't. So one interpretation in the original in statistical mechanics was that, well, you could have, can you see this? Two systems, J and K. And then subadditivity says that the entropy of the joint system is less than the sum of the two entropies. And equality does not hold when the systems are separated, because separated systems can still interact. Inequality holds when they don't interact. Then you can ask, well, what if they overlap? Then if they overlapped, I've counted the intersection twice, once with J and once with K, and strong subadditivity says you can subtract the overlap, only count it once, and it's still true. Okay. Then it turns out, by the way, is this distorted because it's, I mean, it doesn't matter if it's distorted on the windows, but okay. There are a number of reformulations of strong subadditivity, and relative entropy is very useful to produce that. So you have two positive operators defined as trace of P log P minus P log Q. And one of the properties is that it's monotone under partial traces. Okay, if you've got a composite system, then you take a partial trace, the relative entropy decreases. Now, if you look at the relative entropy, and I'm always going to suppress tensor products with the identity between a state on BC and it's the reduced state on rho C, well, the relative entropy you can write out as trace rho BC log rho BC. That's simply minus the entropy. And this term, you don't have any C here, so I can just take the partial trace over C, be left with rho B, and then I get precisely the entropy of rho B. So if you realize that this combination, which is minus the conditional information, is this relative entropy, then you can rewrite relative entropy as a special case of the monotonicity of the relative entropy under partial traces. And if you substitute in what you have here, you see this, except you just switch the sides, you get strong subadditivity. And I've essentially written it as an inequality for conditional information. Now, there are a number of equivalent properties that go one or two lines, and I will concentrate on the first one. And these are now, I think, in modern textbooks, all considered basically strong subadditivity. The relative entropy is jointly convex in P and Q. It's monotone under partial traces, and it decreases under quantum channels or under quantum noise. And those are the important ones. There are some others, but I will focus on the joint convexity of the relative entropy. And the fact that joint convexity, the only thing I want to emphasize that in terms of these equivalents implies monotonicity under partial traces goes back to an idea of Armin Ullmann in 1973 when we were trying to prove strong subadditivity. He was also, and he was working quite isolated independently in Leipzig, and he realized that you could take the partial trace by integrating unitary operators over Haar measure. And he came very close to proving strong subadditivity. It's interesting, there's a small industry of simple proofs of strong subadditivity, and a year or two ago, I got one from Gromov, who had rediscovered Ullmann's formula. And if you want to be more pedestrian, you don't need to integrate over Haar measure. You can simply take the Weyl-Heisenberg operators, conjugate with the Weyl-Heisenberg operators, and add them up. That's simply a discrete version of what Ullmann did. Okay. And the other equivalences are easy to show. Some of them are trivial, some of them take 2 lines. The conditional information played a key role, and in fact, I started by saying to Elliot, gee, we could prove strong subadditivity if we could prove the conditional information was concave. And he said, don't be ridiculous. I mean, it's a difference of 2 concave functions. And then he gave me a counterexample. And I went away and I came back and I said, the counterexample is not a counterexample. And then I went off hiking for the weekend, and we got up at 5 in the morning, we climbed some mountain, I got back at 11 o'clock the night, and I walked in the room, he must have been calling every 20 minutes. And we now know that this concavity of conditional information is a special case of the joint convexity, but you know, conditional information is always positive for classical systems. But for highly entangled quantum systems, it can be negative. And for a long time, that was thought to be, we say in the original paper that that's a defect of quantum systems. It's not a defect, quite the contrary. You simply go back to the information theoretic interpretation that, roughly speaking, conditional information is the amount of information you need to transfer to learn about a joint system when you know about a partial system. And when it's negative, it simply means that you have more information than you need. You have these additional correlations that you can save and use for future information transmission. And a very precise mathematical and elegant formulation of that was made in 2005 by Horodetsky, Oppenheim, and Winter with a process called state merging. Now, I want to talk briefly about what is now called purification and an alternate version because it plays an important role and again connects to the conditional information. It's well known and not hard to prove. It's simply the singular value decomposition that if you've got a pure state, then the reduced entropies are equal. If you start with a mixed state, rho A, B, C, you can always extend the system so that you have a pure state. Psi A, B, C, D, and now that you, okay. And now if I write down strong subadditivity again, and I replace the terms that have A using this identity so that entropy of rho AB is the same as the entropy of rho CD, then I get what's called weak monotonicity, okay, or monogamy of entanglement, because basically this is the sum of 2 conditional informations, one between BC and rho B, and one between CD and rho D. Conditional information can be negative, but both of these cannot be negative. So quantum mechanics is a very Puritan theory. Charlie can be tangled with Beverly, or he can be entangled with Dorothy. But Charlie is not permitted in quantum mechanics to be entangled with Beverly and Dorothy at the same time. Okay. Now, if you look at this quantity here, you see that, again, if rho BCD happens to be pure, then these 2 terms will be equal, and these 2 terms will be equal. So this, you'll get equality here on the left-hand side, but the left-hand side is sum of conditional informations, and these, if they're concave in rho BCD, then the sum is a concave function, and the sum has to be bigger than 0, and that was really the basis for the first proof. But we had to go through some work in order to get there, and one was for me to bring to Elliot's attention. He kept saying, well, can't you do this, can't you do this? And I discovered that one of the things Yost and Bauman had done, not strong subadity in the 2x2 case, but something related to it, and they had also looked at something called the Wigner-Yanase-Dyson entropy. So Wigner and Yanase wanted some measure of what they called skew information with respect to an observable K and a density matrix. And so they defined the skew information, the trace of the commutator of K and gamma to the P. They actually did square root and K of gamma. And you work this out. This is K, gamma to the P, gamma to the 1 minus P, minus a linear term. And for t equal to 1/2, they were able to prove concavity, simply like for the normal entropy. And Dyson said, well, you know, why stick with 1/2? You can use any t, oh, I have p here, should have been changed to a t, in 0 and 1. And if you read the original paper, and also Leaves' paper, they say that the limit as t goes to 0 and 1 gives the usual entropy. But if you look here and put p equal to 0, that's just get the identity here, and you just get gamma here, and by the cyclicity of the trace, you get 0. Now, Dyson certainly knew better, and somehow this slipped up when the paper was written, that you need, in order to take the limit and recover the actual entropy, to replace the 1/2 by this fudge factor of 1 over t times 1 minus t, so that you have 0 over 0, and then when you take the limit, you do recover the usual von Neumann entropy. So what became known as the Wigner-Yanase-Dyson conjecture was to show that this quantity is concave in gamma, and Elliott Lieb, in a celebrated paper, proved that. And he did the obvious thing, what any reasonable person would do. You want to prove concavity, you don't care about the linear term, so he dropped the linear term. And he also proved something more. He didn't require that both of these be the same, so I'll write it in this way. He proves the joint concavity of k star p to the t k q to the 1 minus t. Now, in a paper that was not really noticed at the time, not until much, much later, or at least not by very many people, Ando gave an alternate proof of this joint concavity. But he noticed something else. He noticed that for t between -1 and 0 and t between 1 and 2, it changed from convex to concave. Outside that range, it's neither. Now, it turns out, but it wasn't noticed until Hasegawa in 1993, that if you include the linear term, you put the linear term back in, and you put in this fudge factor in front, then you only need one theorem. This t and 1 minus t, they change sign at 0 and 1, so you get convex to concave automatically. And if you can prove that this quantity is jointly convex, in the full range -1, 2, you immediately get that. And I rediscovered that in 2010. You could take a limit, so Lieb's long chain of inequalities, which led to the original proof, were brilliant. But in fact, if I think Wigner and Yanase had not left that fudge factor out of their paper, and then you might not have dropped the linear term, and we might have seen immediately that simply taking the limit gives you the joint convexity that you need to immediately get strong subadditivity. The next key development, and really the clue to simple proofs, was that Araki, he wanted to generalize things to type 3 von Neumann algebras which don't even have a trace. And I'm going to give you the pedestrian version. Namely, look at the d by d matrices, so we'll stick finite dimensions. You can use the Hilbert-Schmidt inner product, and now we define operators on the space of matrices by to fixing p, and you simply multiply on the left by p, and then r sub q is multiplication on the right by q. And the nice thing about this is that even if p and q don't commute, the left and right multiplications do commute. No matter which order you do them in, you end up with pxq. And these left and right multiplications have all the properties of p and q carry through. If p and q are self-adjoint, so are these operators. If they're positive semi-definite, so are these operators. Left multiplication by the inverse is the inverse of left multiplication. The log of right or left multiplication is right or left multiplication by the log. So all these properties carry through. And this allows you to define the relative entropy. So if you had started, if you were a classical information theorist and said, oh, how should I generalize the Kullback-Liebler divergence, which is basically P over Q? Well, it's not clear for non-commutating operators. You know, this could be P Q inverse, or it could be Q inverse P, or you could have lots of more complicated things with minus 1/2. But if you take the trace of log of left multiplication by P and right multiplication by Q inverse, these commute. So you can just use the property of the log to separate them. And then it's the same as left multiplication by the log. And I'll use the cyclicity of the trace. You get exactly the relative entropy. So this very deep idea, which Araki introduced for von Neumann algebras, which don't even have a trace, in finite dimensions actually lets you give very simple proofs of joint convexity and strong subadditivity, and joint convexity of the Wigner-Dyson entropy. But it took me 25 years to realize this. There were other people, most notably Petz, but others who realized that you could get simpler proofs of strong subadditivity using this, but I was avoiding von Neumann algebras at the time. And Petz also realized that you could generalize the relative entropy by replacing x log x by any convex operator function. And if you don't know that, it means you write down the usual convexity inequality, and it should hold as an operator inequality. And this is related to monotone operator functions. They have a nice characterization. Okay, I'm not doing too badly on time. And here's the definition. You have a square root of q p star. You make that. This is just to make it positive semi-definite, and you simply take the function of LP RQ inverse. So in addition to being operator convex, the function should be 0 at 1. And it turns out that if G has this property, so does xg of x inverse. And the effect when you substitute it into this quantity is to reverse the order of Q and P. So x log x gives you the usual relative entropy, and minus log x also gives you the usual relative entropy, but with P and Q in the opposite order. Okay. Now, let me point out that with the linear term back in, if you pick the right function for g of x, and we picked this one, but you could pick this one, the fudge factoring of x minus x to the t, these are convex operator functions, then, and you substitute that in, you get exactly the Wigner-Yanase-Dyson entropy with a minus sign and generalized to a q, okay? And the k, you take the limit, and for 1, if key is equal to the identity, p log p minus p log q, you get the usual Dyson entropy. But it's very important that you have the linear term there and the fudge factor. Okay. Now, it turns out that convex operator functions have very nice integral representations. And I won't go through the theory of that. It's actually very relevant, and I'll mention it again later, having to do, basically, it's a theorem that a function is a convex operator function if the divided difference is a monotone operator function. And monotone operator functions basically can be extended analytically to map the upper half plane to the upper half plane. Okay. And that leads to nice integral representations. And for particular functions, you can write them down. The critical thing is that the integral won't necessarily converge unless I include this term, but for convenience, I'm writing in slides, I put it as a separate integral. That at the end of the day, when you work this out, you get k star p 1 over L p because URQ, pk, and then the same thing with q and p reversed. And now k has to be fixed, okay? But if k is fixed, here I have a kp, then to show joint convexity in p and q of this quantity, it's enough to show that each term in this integral is jointly convex in p and q, which is equivalent to x, p, q being that map to trace x star 1 over L q plus this should be URP of x is jointly convex. And now I'm going to give you that proof. Because this is a homogeneous function, we don't need the convex weight functions. We just need to prove that f of the sum is bigger than the sum of the f's. And we start by the observation that if you have trace of m star m, or which I could write as an inner product with the Hilbert-Schmidt, it has to be positive. And I'm going to choose for m something to the minus 1/2 acting on x, minus something to the plus 1/2 acting on lambda, which I have not yet chosen, but will tell you about. And it's easiest to see, I think, in the inner product form. These are self-adjoint operators, so I can flip this minus 1/2 over to here and get x, this quantity to the inverse x. The cross terms, when you flip them over, are clearly seen to cancel, and here you get a plus 1/2, you just get a plus 1 here. Okay, so then I have to tell you what you should put in. What you should put in these parentheses is what's in the denominator in that integral, or in the quantity we're interested in, LP plus URQ, okay? And then you put that into the expression and you have something positive. And to prove convexity, we take a bunch of things like that and add them up. So we have 0 is less than the sum of these mj's, and I explicitly put in the u dependence because I'll need it later. So we get the first term, which is basically xj star inverse xj, and then we have the two cross terms, and then we have lambda star, and here we can pull the sum inside because there's the trace is a linear function, and the xj's only occur once, okay? Or here it only occurs. We can pull things inside. And now you just have to pick a clever choice of lambda. And I choose lambda to be 1 over this bunch of stuff acting on sum over j of x sub j. Now you can see that if I, for example, put that into here, what I get is the trace of this sum, 1 over this stuff, and then I've got this term. The same thing happens for the other cross term. For this term, the inverse, you have one of these from lambda star and one of these from lambda. The inverse cancels, or this cancels one of the inverse and leaves you with the other inverse, so that at the end of the day, these last 3 terms are exactly identical and have the same sign. So 2 of them cancel out, and you're just left with one of them, and writing it in this form, you get that 0 is less than the sum of this stuff minus the trace where the sums are on the inside. That is exactly the joint convexity that we wanted to prove. And what I like about this argument very much is that if you teach linear algebra or calculus, you typically teach the Schwarz inequality for numbers. Sum over k of ak bk is less than or equal to the sum over k of ak squared, sum over k of bk squared. And I just pick for ak pk to the 1/2, bk to the minus 1/2, and with little manipulation you see that I can write the inequality for numbers in precisely the same form. And when you prove this in your linear algebra or calculus course, you basically say, well, we look at this sum over k of positive things. It has to be positive. And then I simply differentiate and choose lambda to minimize. I gave you exactly the same argument for operators. You just have to be careful to keep things in the right order and to make a clever choice for your operator lambda. You don't even, to prove strong subadditivity in this form, you don't even, and as far as the integral representation goes, if you're only interested in the logarithm, it's easy to write down an integral representation that any calculus student can check. You don't even need to know the elementary Schwartz inequality. You simply imitate the proof that you give in your elementary courses. And actually, Elliot Lieb and I knew that, and we had an operator form. It was really an operator inequality. It didn't require the trace. And we could prove some special cases, but it wasn't enough to prove strong subadditivity. Okay, this alone is not enough. You need to have this deep idea of Araki's with the relative modular operator, and then you get something very simpler. And so after we proved strong subadditivity, we had this inequality left. And I said, well, tell you being young, and I said, I guess we should write that up and publish. He said, well, that's so simple. I mean, probably lots of people know this inequality, so maybe it's already known. So, okay. So we asked a lot of people, and no one knew, so we wrote it up and published it in 1974, and there were some other later papers in linear algebra with alternate proofs that they claimed were simpler, which was hard for me to understand because our proof was basically 2 lines. And till in the summer of 2010, I was sent a paper to referee, and I started reading the introduction to this paper, and lo and behold, it said that the joint convexity of X star P inverse was proved by Kiefer in 1959 and rediscovered by Lieb and Ruskai. And I went to JSTOR, and indeed, Kiefer proved it in 1959 in a paper in the Journal of the Royal Statistical Society on experimental design. And we have been talking to people in matrix theory, people in operator algebras, but Kiefer in 1959 already knew it. So it wasn't a new theorem. We just didn't know it wasn't new. Now, Isaac Kim published this amazing paper in which he had an operator version of strong subadditivity. You notice if you would take the trace over C, then the entropy combinations you would have here would exactly give you strong subadditivity. But we only have the trace over A and B. This is an operator inequality over C. And somebody told me about this when I was visiting IQC, and I said, I don't believe it. That can't possibly be true. We went to, he gave me the reference. I looked at it. We went to breakfast the next morning, and I explained to him why it was wrong. And so I thought, well, I should write to this poor graduate student in Caltech, and I wanted to be tactful. So that evening I sat down to prepare my email message, and I looked at his paper again, and I thought, oh, he's right. And the next morning I gathered a group of people together and explained the argument to the end. It's not properly a new proof of strong subadditivity. What you do is you prove it by revisiting the old proof, which is with the relative modular operator, which is why I went through that. And now, if you recall, we have the joint convexity of the monotonicity under partial trace. That's true if you have the K there, but the K, there's no monotonicity under the partial trace of KABC. It has to be the identity tensor BC. And so now I will just rewrite that using this definition in terms of the modular operator with left and right multiplication. And now in order to compare things, I want to have a trace over ABC here. I can easily do that by leaving everything as B and C, but changing Q to QABC, because if this one partial trace will just reduce QABC to QBC. Okay, and then the next thing to do is to choose KBC to be the identity tensor KC, and to choose PABC to be PAB tensor IC. Okay, this only acts on C, this only acts on B, A and B, so these commute. And it doesn't really matter if you do the left multiplication before or after, so you can pull the KC through. And so now you can write your monotonicity under partial traces with the KC here. Then you've got G of this relative modular operator QABC. And now the next thing that Kim Real did was to choose KC to be a rank 1 projection. Okay, it's a rank 1 projection, so the trace over C simply becomes an inner product on C. And this is arbitrary, it's true for all phi C, so it has to be a positive operator. And so you have this very general operator inequality for convex operator functions. And you apply it the way I did it. I use g of x equal to minus log x. And you get this operator version of strong subadditivity. If I had used x log x and interchanged the roles of p and q, that is equivalent to getting the adjoint. And since this is a positive operator, of course, its adjoint is also positive. But you can also get this inequality simply with the row ABC on the other side the same way. If I use x log x, but don't switch p and q, I get a new inequality. And it's a strange inequality because if you look what's in the square brackets, it's the same. Here I have plus log row ABC, here I have minus. The two square brackets are exactly the same except that they have the opposite sign. It looks like strong subadditivity going in the wrong direction, but here I've got the trace of AB, row AB, not row ABC. So you don't get strong subadditivity by taking a partial trace over C. It's not at all clear to me what you would get if you took the partial trace over C. It is, I think, an interesting question. Kim had some applications for the original inequality, and the question is, are there applications where you can use this pair of inequalities together to get upper and lower bounds? I don't know the answer to that. You can also, with the proper choice of G, get an operator version of the Wigner-Yanase-Dyson inequality. And you notice there's no linear term here. You need the linear term in order to prove joint convexity and monotonicity under partial traces, but then they cancel out. So you can get inequality. And there's been a new appreciation of this work. In 1973, I gave a talk at a UPAP meeting, and the session chair asked afterwards, he said, well, that's a beautiful theorem, but what good is it? And so I went away and worked on other things for 20 years. And then about 1995, I started getting email asking me about strong entropy and strong subadditivity. And in particular, one of the questions they asked is, what are the equality conditions? And for subadditivity, the equality conditions were simple. You just needed a tensor product. Here, it's not hard to see that if you had row A be tensor row C, you would get equality. Or you could have row A tensor row BC. Either of these will give you equality, but it turns out that they are not necessary. And to find the necessary and sufficient conditions for equality, you go back to this Schwarz inequality proof, and you realize that all of the terms have to be positive, which means that all of these mj of u's have to be positive. And you can write it out and translate. It gets kind of messy. But the point is, they have to be positive for all u in 0 infinity. So whatever the equality conditions are, they're essentially independent of the function g. Okay? And what are the equality conditions? Well, the equality conditions here, I could put the B with either the C or with the A when I took the tensor product. What you can do is you can say, well, I don't want to make that choice. I'll split, suppose the Hilbert space HB is itself a tensor product. Then I can put part of the B with row A, so I have row A B prime tensored with row B double prime. Okay, and you can check that that works, and it turns out that you can take a direct sum and it still works. And those are the necessary and sufficient conditions. The sort of abstract form was worked out early on by Petz, and then when, after Mike Nielsen asked me, I worked them out, but the implications were not clear, and in 2004, the fact that means that the function has this form was worked out by Hazen, Yosa, Petz, and Winter, and of course the inequality conditions are the same for Kim's functions. There are a number of reasons why this is important in quantum information. I want to mention one is something called the Holevo bound, which I won't explain for people who don't know it. But Holevo proved this. He gave a very long and complicated proof. Again, like Ullmann, he was working alone in Moscow, and he didn't know anything about strong subadditivity. It hadn't been proved yet. And it was a brilliant piece of work, which was also not appreciated for over 20 years. And then when people appreciated it, they realized that it could be done as a two-line corollary of strong subadditivity, although that by no means diminishes his work, and in quantum information theory, he's done tremendous work. There are lots of applications in channel capacity, and I find it very gratifying to actually have a paper which says that strong subadditivity, and this is not paper by me, okay, is the key result on which, so there is, there are uses for this. It just took a long time to discover them. Now I want to mention briefly another new convexity inequality, because it goes back to my first meeting with Freeman Dyson. In the paper of Lieb, there was a long chain of convex trace functions. What's happening with this thing? I'm probably loud enough to not use the microphone. And one is the trace e to the k plus log p is concave, which is rather curious because if these commuted e to the k, you would just get trace e to the kp. It would be linear, and there's no obvious reason why it should go in one direction or the other, but it is in fact convex. And Ullmann, again working alone in Leipzig, independently realized by the argument I gave you before that if you could prove this, you could prove strong subadditivity. He had a completely different argument. And soon after Epstein's work, or sorry, Lieb's work, Epstein gave an alternate proof of Lieb's inequalities using the theory of Herglotz or operator monotone functions. He looked at the function that you would have to put a perturbation in to prove convexity by differentiating. And he told me about this, and he gave me a paper. And when he sketched it, I sort of could roughly follow what he was doing, but he gave me this paper. It was absolutely incomprehensible. And a week or two later, I was in New York for a meeting, and I was going to spend the next day during New York, and Andrew Leonard convinced me to come to Princeton and meet Dyson, who was very kind to me. And I mentioned this to him, and he said, well, that's very interesting. And I gave him the paper. He actually put me up overnight, and in the morning over breakfast, he explained the argument to me. And the point is, Epstein's paper must be read backwards. That there are all these things, for most of them, the results are complicated, but for this particular one, it's very simple. And recently, I got some email from people saying they wanted to prove this slight generalization, and they couldn't get things to work, and I immediately said, oh, you should use Epstein's method. And indeed, that works. So I guess my time is up. Let me mention briefly, strong subadditivity looks like the first in a long chain of n-party inequalities, and Lieb basically showed that the natural generalizations were false. However, a recent development in classical information theory is that Jung and Zhang have found new four-party inequalities that are independent of what they're called non-Shannon inequalities, and there's a whole industry of this which I will skip over. It seems to be a very, very hard question to extend these to quantum states. We can, in fact, say something about the inequalities for stabilizer states, but I'm going to skip over all of that. And This leads to a large number of open questions, but basically these open questions boil down to, are there new what you would call von Neumann inequalities for quantum entropy? If there are, then we would truly have inequalities that were stronger than strong subadditivity. And I think the key to proving this is that we need better parties. Because when I was a graduate student, I was always fascinated by the picture on Hirschfelder's wall. And I don't know if you can see clearly what this is. Von Neumann's daughter has assured me that not only is it a pineapple, but he wasn't standing in front, it was on his head. And I always thought, boy, those people at the Institute, back when von Neumann and Dyson were there, had really great parties. And I think maybe that's why I wanted to become a mathematical physicist. And unfortunately, we only have a pathetic imitation. We need better parties if we're going to prove stronger theorems. Thank you.
Right, thank you. It also shows that we probably need pineapples to celebrate parties. Actually, incidentally, Philip yesterday said that Dyson was probably the one to start the field of operator research. And what you have discovered by the old paper was actually somewhat related to operator research, optimum experimental design. So
yes.
It's
Yeah, I mean, when you look at this, you can see that there are connections everywhere in this subject.
Right. Any questions? I somehow noticed that a lot of the younger researchers are not asking questions, so perhaps you should ask questions. I think you should not. I think if you find this 80% incomprehensible, that's fine, because the rest of us who are supposedly expert also find 80% incomprehensible.
Well, I went.
But you should ask questions.
Yeah, I will be happy to answer questions, either publicly or privately, but can we have one?
So does the second law still hold for quantum entropy? And if so, what's the physical interpretation?
The question was, does the second law hold for quantum entropy?
Yeah.
That right now at the National University of Singapore, there is a workshop going on in which they are studying that. It's a subject of very active research, and they are studying exactly that question.
Raiha is leading. The person behind you. Yes. No.
So, but there is a workshop at National University of Singapore right now, and there are several. It's an active field of research, and there are different opinions and different approaches. It's not a question I can answer, and it's not a question that can be answered. But it is an interesting field of research, and you should go over and talk to those people if you're interested.
Right. Yes.
You mentioned you re-derived the result, and I was just wondering which paper is being cited more.
That's an interesting question. You know, the strong subadditivity paper is my most cited paper, but it's rarely, I mean, you know, when an inequality reaches a certain point, this is, I think, an indication of why these, you know, citation counting things and whatnot, because most papers in quantum information theory do not cite the original strong subadditivity paper. They either think this is so well known they don't bother with the citation, or they cite Nielsen and Chang's textbook, or perhaps Vail's review article in Reviews of Modern Physics. So, there's a small industry of simple proofs. So I think in terms of citations, it's very variable, and it shows that simply these citation countings are not necessarily indicative of the value of a result or a theorem.
Right. Any other questions? So if not, we thank Mary, Beth, and